Hey guys, all right, let's talk about our standard reduction potential. So, standard reduction potential the main apps that we're going to soon, but we'll talk again about the effects that the have, similar to how we talked about the previously. So, let's go. So, standard reduction potential. So, when we talk about our voltaic cells, that's 4, and Zn goes to Zn2 plus 2e minus. We have Cu2 plus 2e minus going to Cu. The Leo on the left occurs at the anode. The electrons leave the anode to go to the cathode. The cathode is at the reduction, which is right, cat. We also have our salt bridge, which allows the cell to stay electrically neutral while we're doing this. That is a spontaneous cell. Go awesome. That's really awesome. Now, if you look right here, you'll see that this one is backwards. We have copper on the improper side, and we have a plus 0.34 volts, and the zinc is 0.70 volts, and that means that this is a 1.10 volt thing, and all those numbers mean like nothing at the moment. But that's what we're going to be talking about, is how we get those numbers. So let's we talked about this last time, the fact that we need to have that because we cannot get electrons to flow if we're going to generate a net charge on either side, be it positive or negative. That won't happen. So the reaction will not occur without some charge. Okay, so we're talking about cell potential standards. So electrons flow spontaneously one way in a redox reaction, from high to low potential energy. Okay, awesome. The potential difference between the anode and the cathode in a cell is called the electromotive force. So it's how much force there is for that electron to flow. It's also called the cell potential, and it's designated as E cell. Okay, that's the way we designate them. They're always listed as reductions. These values are independent of the stoichiometry. So unlike what we did with our chemical equilibrium, if we multiply this reaction, those values are not going to change. So this is a different situation. So these values are not going to change if we have different stoichiometry. That is not true when we talk about chemical equilibrium or any of the stuff that we're going to talk about for exam 3. So all of that stuff is very dependent on the stoichiometry that we've written. Our cell potentials are measured in volts. 1 volt is a joule per coulomb. Reduction potentials for many electrodes have been measured and tabulated. You'll see that on your exams. Okay, those tables are available to you on the exams. The values are compared to the reduction of hydrogen as a standard. So we always look at the reaction of 2H plus 1 molar plus 2 electrons going to H2 gas, 1 atmosphere. That's a standard hydrogen electrode. We call it a She. This is our reference, and everything is measured against that. So that's our standard hydrogen electrode. So if you hear me say She or standard or whatever, that's what we're measuring it against. By definition, that standard is given a reduction potential of 0 degrees or 0 volts. And that's because that's our standard. So we're not going to measure a potential, only measure. Okay? So that's our standard. Yay! Awesome. Now we know what we're measuring against. We know what all of these little things mean. Yahoo! And I swear it won't do anything. Okay. So standard electrode potentials. Well, this is awesome. So I have a table right here. It says F2 gas plus 2 electrons goes to 2F minus, and that has this E of 2.87. Awesome. So that cell potential is 2.87 for that half reaction. Okay. You'll see that each one of these has a value. These are positive, these are negative. Okay. That's cool. Everything has a value. They're all listed as gain electrons reduced. So they're reduction potentials. So you may see them standard reduction potentials. You see that listed right there. It isn't always listed. These are just two different tables. So this one has some values that this one doesn't. That's why you see both of them. Okay, awesome. That's because I wanted to do some stuff with things that weren't on. Now, when we go to do things with standard cell potential, for standard conditions, we can use the following to calculate E cell. So the E standard for the cell, that's what that little circle means, standard. This right here, little circle right there. Standard cell potential equals the standard reduction potential for the cathode minus the standard reduction potential for the anode. Now remember, everything that's in this list is a reduction potential. Okay? So all of those numbers are for reductions. As long as we're using the reduction values, then the way that we calculate that is with this equation. If the value of E cell is greater than 0, then it's a spontaneous reaction. It's going to happen no matter what we do. We can use that to make a battery. If it's less than 0, it's going to require work, us to put energy in to make that reaction go. Now, that doesn't mean it can't happen. It just means it takes work for us to do. For the anode in this cell, as it's written, E naught reduction is negative 0.76. Okay. For the cathode, E naught reduction equals 0.34, right? And so if we wanted to calculate the E naught for the cell, the E naught cell equals E naught reduction for the cathode minus the E naught reduction for the anode. So the reduction for the cathode, which is this line here, the 0.034 volts, minus the negative 0.76 volts. And we find that that comes out to 1.10 volts, which is positive, so this is a spontaneous reaction. Awesome. Here's the other thing. Now, I know that when I'm looking at a table like this, that this is not a physical possibility. I can't have two reductions. And so we could reverse one of these reactions. When we reverse it, the value for the E is the same number, but a different sign. So if it's written here as positive, and instead of going from SN4 plus to SN2 plus, which is a sign SN4 plus 2 electrons, goes to SN2 plus, which is 0.15. If I wrote it as a SN2 plus, going SN4 plus 2 electrons, that would then be a negative 0.1. Now, calculating in both ways is fine, but you have to remember which way you're going to do it, okay? So if you're always going to use the values out of the table as they exist, use this one and make sure that you subtract the anode, right? Because that's the one that's the oxidation, so you have to subtract what's supposed to be in the reverse direction. The other thing that you can do is just write it down the other way. So when I look at this, I see that one of these is 0.34 volts, and that is cathode over here, 0.34 volts. And then my anode over here, the way it's written, is plus 0.76 volts. And so when I add them together, that gives me 1.0 volts. Okay, so notice that I changed the sign on the one that's written as an oxidation and not reduction. Okay, so that's how I handle that. That works better for me. I don't care how you decide to do it, as long as you do it in a way that gives you the right value. Okay? So you will be questioned about what is the right equation. Okay, so you will need to see that. All right. So calculate E naught cell for oxygen. Ooh. I'm sorry. Calculate E naught cell for oxygen, converting to hydrogen peroxide, reacting with Mg. Okay, so we want to talk about oxygen going to H2O2 and reacting with Mg. Okay, let's go look at our tables. So oxygen going to H2O2. So I'm going to look for H2O2, and I see right here 0.70 I see O2 gas. Hold on. So I see that this right here is O2 gas plus 2H2 liquid plus 4 electrons. Gives me oh, wrong line. O2 plus O2 gas plus 2H plus 2E minus, and give me an H2O2 quiz. As written, that is 0.70 volts. When you look at the mg, I always do this. Mg2 plus, and I'm just writing down the reaction as it's written here, plus 2E minus. It's going to go to give me Mg solid, and that is negative 2.37. Now I know from what's been written, I know that this reaction right here is going to occur in the other direction. So Mg solid going to Mg2 plus, because it says that I want to react oxygen converted to hydrogen peroxide reacting with magnesium. So I know it's going to go in the opposite direction. If that's the case, then I know that my E naught cell is equal to the E naught reduction for the cathode minus the E naught reduction for the anode, which is 0.70 minus negative 2.37. And that gives me a nice positive of 3.07. Okay. Positive value, I know that's spontaneous, it'll happen on its own. That's cool. That's impossible. I also want to calculate the one for SN2 plus NZN. Okay. SN2 plus NZN. Alright, I see SN2 plus is here, so I have a reaction that says SN4 plus 2 electrons gives me SN2 plus, and that's 0.5 volts. And then my ZN, oh, it's right there. ZN2 plus 2 minus ZN solid, and that value is negative 0.76. Right? So it says SN2 plus ZN. So that means I want this one going the other direction. It's actually not going to be SN2 plus, is it? Okay. If I want this one going the other direction, that means that we're going to be looking at an E naught reduction for the cathode, 0.15 volts, minus the E naught reduction for the anode, 0.76. And that gives me 0.15 minus and then 0.76. Give me 0.91. Sweet, wasn't that fun? And then I want to talk about Li and F minus. Okay. So F2 F2 plus 2E minus goes to F minus, and that's a 2.87. And if I look all the way at the bottom, I see that Li plus an electron gives me Li solid, and that's negative 3.04. Now it does say that we want to react Li plus and F minus. Okay. And so I'm looking at this going, okay, well, I think that this is going to happen as the F2 plus 2 electrons minus 2.7, and the Li solid going to give me Li plus an electron, and that's 3.04 if I reverse it. Now, if it's going to be spontaneous, that's what I'm going to have to do. 2.7 plus 3.4, which gives me 5.9. Now, if I had intended this to be the other direction, F minus, with Li solid, which is not what I wrote, but I think is what I meant, then we would be looking at reversing. I can't do that. That's what it is. Okay. So rather than doing this way, what we're talking about, not that direction. I want to react that F minus. F2 plus 2E minus plus F minus. Nope. I can't write that one. F minus goes to F2 plus 2E minus. That's negative 2.87. And then the Li plus an E minus going to Li solid. And that's negative 3.04. So negative 3.04 minus 2.7. And that gives me negative 6.01. Now, that's the way I asked that it be done. And the reason that I did that is because I wanted you to see that it's not a positive. Okay? It is a very negative. And going the other way, that's a very favorable reaction. But taking that F minus and making an F2 and taking that Li and adding an electron to it, neither one of those processes are desirable. We are moving electrons in a way that they do not want to be moved. So that is not something that's going to happen without a lot of work. And so we have this. It can be done. We can calculate what that value would be, but it's going to be a lot of energy. Okay. Now, I did that last one as the alternative. So I said, okay, this is the one that I'm turning around. So I changed the sign on it and I added them together. Okay. The other one I did with the subtract the negative. Either one works. You just need to make sure that you're consistent in what you're doing. The way it should be. Okay? And we talked a little about oxidizing and reducing agents. The more positive the value of E0, the greater the tendency to reduce under standard conditions. The strongest oxidizers have the most positive reduction potential. The strongest reducers have the most negative reduction potentials. Reducing agent causes reduction in something else. Oxidizing agent causes oxidation in something else. A material on the left of a half reaction will react with any material below it and on the right. Okay, so again, if we're talking about a table like this, talking about anything on the left will react with anything below it and on the right. So the Cl2 can and will react with an Ag. Okay, can and will because it's above it. And can aluminum ion reduce lithium solid? Okay, so my lithium ion. That's right here, lithium ion. Oh, wait. Oops. Oh, Al3 plus. Can aluminum ion reduce lithium solid? Yes, it can, because the aluminum is above the lithium. Aluminum here, lithium on the other side below it, that'll work. What about the lithium ion? Can it work on that? No, it can't, because that would be two reductions. Can't do that. So what can it reduce? Well, the only thing it can reduce is this one right here, that LI based on this table. That's the only thing it can do. Okay, awesome. So much fun. Questions, comments, problems. I hope that there are no questions, comments, problems, but if there are, please come through the normal channels, email, phone, come to my office. Let's talk. Let's see what we can figure out. Because I don't think that this should be you beating your head against it. I do think that there are ways that we can talk about this and get you where you need to be. It's material, but we can manage. Okay? So now we're going to do some practice with standard reduction tensions. Okay, what kind of practice are we going to do? Let's see. In these problems, assuming you have either the solid, liquid, or aqueous solution called for in the table to produce a spontaneous cell, provide the following. Overall reaction, the anode half reaction, the cathode half reaction, the cell notation, and the E0 cell. Fluorine gas and lithium. So that's what I'm looking for. I'm going to go back. Let's do this. So I want to talk about fluorine gas, which is F2, and Li. So those are the ones. I'm going to pull this over to the side so we can pull over our reduction potential table. Table a bit. So when we look, F2 is up here, and that's a 2.8. So F2 is 2 electrons, plus a 2 F minus 2.87 volts. When we talk about Li solid, okay, that's this one down here. So we have an Li plus an electron, plus the electron. It's the Li solid. That is, as written, negative 3.04 volts. And so we would take the E0 for the reduction at the cathode minus the E0 for the reduction at the anode. And that's equal to 2.87 minus negative 3.4. And that we can do. So 2.87 minus the negative 4. Also calculated on, isn't that right? And that gives me that 5. I thought it calculated this, which I had. Ooh, that was fun. Lead and manganese. Lead and manganese. Okay. Let's find lead. I'm looking for PB, and I see a PB2 plus 2E minus going to PB, and that's negative 0.13 volts. And the other thing I was looking for is manganese, which is Mn. So do I see N, Mn, N? I see it over here. So Mn2 plus 2E minus to give me N. And of course, that value is here, so I find it, and that's negative 1.18. In order for this to be a positive, we know that we're going to have to do the PB2 plus going to PB and the MN going to MN2 plus. That's going to have to work if we want to do this. So if that's the case, then I'm going to take the negative 0.13 minus the negative 1.18. So I'm taking E naught reduction for the cathode, which is this one, and because reduction occurs at the cathode and oxidation occurs at the anode. So that's why I have that written. And if I do that, negative 0.13 minus the negative 1.8 gives me 1.05. And that is positive. So that will happen the way that it is. Okay. Oxygen in acid and mercury. Okay, oxygen in acid. Oxygen in acid is 0.68. So oxygen O2 plus H2 plus 2E minus. That's something I want. That's not. Where is it? Sorry. First I picked the peroxide one, which is not right. Ah, there we go. 2 gas plus 4H plus 4 minus 2H2 liquid. And that value is 1.23. So it's right there. Right there. And mercury, which is Hg. So I see Hg. Find Hg. It's gotta be this list. It's up there, maybe over here. Of course, I went up. I see. So I have Hg2 plus 2 electrons going Hg2 2 plus, and Hg2 plus 2 electrons going to Hg. I suspect that the one I'm looking for is the one with the 2 Hg liquid. So Hg2 2 plus 2E minus, and give me 2 Hg. And of course the value on that is 8. All right. Gain electrons reduce cathode, and then lose electrons oxidize at the anode. E naught cell equals E naught reduction cat minus E naught reduction anode equals 1.23 minus the 0.85 because it's positive. 1.23 minus 0.5. And it gives me 0.38. Okay, not great, but still positive. So that will work. Silver and nitrate. Okay, silver and nitrate. I see right here an NO3 minus plus 4H plus. I'm going to write that down. So there's NO3 minus 4H plus 3E minus NO plus 2H2. And that line is 0.96. And silver, so Ag, which is right here. Ag plus electron goes to Ag solid, and that value is 0.8. Okay. Now, it says nitrate and silver. So that implies to me that this one is going to go the other direction. If it goes the other direction, then we're going to have 0.96 minus 0.80, because I reversed the sign on the 0.80. So 0.6 minus 0.80. And that's 1.6. Wait, oh, 0. Sorry, my decibel's in the wrong place. Don't ever trust me. Much better. Okay, so again, not hugely spontaneous, but that's how that works. And again, the last one, I changed the sign on it and I added it together. So if you change the sign, you add them. If you're not going to change the sign, then you need to subtract the one that's happening at the end. Okay, so that's what we've got for that. Sweet, awesome puzzle. We can do a couple more examples. Calculate the standard reduction potential of the following combinations. Okay, so we have 2Ag plus Cu. See if I can do this. Ag plus. So, zoom in on that. It's really hard to scroll. Oh, Ag. Ag. And of course, I can't see that. Go. Awesome. That's a 0.80. 80. And that's for this one. And that's the Ag plus I've written. Then I find the copper one. I'm looking for copper, but going in the direction. So Cu solid going to Cu2 plus. That, because I'm going to inverse it, is negative 0.34. And so adding those two together, 0.80 minus 0.4, which is 0.6. Mg my table over on the other screen, sorry. So I have an Mg solid going to Mg solid into Mg2 plus 2 minus, which is the reverse, so it's the oxidation. That oxidation is 2.71. Fe3 plus to Fe2 plus is this one right here. This is 0.77. And that's 3.8. chromium wire in chromium chloride connected to copper wire in copper chloride. Okay. So chromium, Cr3 plus 3 minus goes to C. That value is negative 0.74. We also have copper. Copper. Cu2 plus. Plus 2 electrons. To Cu. And that is 0.34. So I'm guessing that we're going to be doing 0.34 minus 0. Negative minus 0.74. And of course, it's going to be 4 minus 0.74. Sounds right. It was 1.8. And platinum metal and platinum nitrate. And I know that I found this previously. I remember looking. I remember looking. I know I found it at some point. Things. I didn't actually find the value the last time. I just remember finding it was PT2 plus. And I don't remember where I found it. So I know the copper one is that. We just wrote that. It's not in this. I swear. There we go. PT2 plus 2E minus. And give it PT. That is 1.2. So again, I'm taking E reduction cathode minus E reduction anode, which is going to be equal to 1.2 minus 0.34. 1.24, and that gives me 0.86. That's volts, and that's volts. Okay, so that's how we're going to practice with our standard reduction percentages. Go awesome. Questions, comments, problems, anything with Voltaic. So we're trying to establish what the standards are for these the cells that we've been asking. What are the values? Okay. We're going to take a break at this point and come back in a couple of minutes and talk about our next topic, which is going to be concentrations. All right. See you soon, guys.